Okay, good morning, everyone. Happy New Year. Hope you guys enjoyed the holidays.
Kinda, sir. Good morning.
All right. So today, well, you guys obviously know the topic. It's simple machines. Mrs. Sil would have went over it with you last year in class. So we all know what a simple machine is. It's just a very basic mechanical system that employs these very simple mechanical principles. Things like moments, coefficient of friction, leveraging forces, stuff like that. Okay. Now, in this topic, we're going to introduce a new system, the wheel and axle, and we're going to look back at the inclined plane just on from a different perspective, a system perspective. Where's that? All right, so the first thing you need to know about these systems is there's a thing that we call the mechanical advantage. So with any simple machine, the reason why we use them is because we want them to be able to leverage a certain effort or give us some kind of advantage, some kind of mechanical advantage. Sometimes we might want to use a small force to move or to overcome an otherwise larger force. So for example, with the lever, we'd have some weight, right? And then we'd have the lever coming here. And the fulcrum, of course. Let's say we had a downward force of maybe 20 newtons here, being applied here. And this weight, the weight of this mass that we were trying to lift was about 4 kgs. 4 kg. Let's use the gravitational constant as 10, just for simplicity's sake. So the weight here would be approximately 40 newtons, right? Let's say the effort we applied to move it would be 20 newtons. So how does this work? How does this 20 newtons help us to lift this 40 newtons? Well, it employs the system of the lever, and the lever gives us a mechanical advantage. Yeah. So if we were to quantify the mechanical advantage, we could say that this system doubles our forces, right? Multiplies it by a factor of 2. So that's essentially what the mechanical advantage is. The mechanical advantage says that the way we quantify this advantage, the number, the ratio, is just dividing the load that we need to lift, the 40 newtons, right, by the effort we put in, so the 20 newtons. And in this case, the mechanical advantage is 2. Right, 2. And it's just a number, it's a unitless number, but it gives us information. It tells us what the system does. Right? So that's the first formula you want to look at. The mechanical advantage of a system is equal to the load divided by the effort, and that tells us what kind of mechanical advantage we gain. Right there in the name, right? Another important property of a system is the movement ratio, or was sometimes known as the velocity ratio. But thinking about it as a movement ratio is much simpler. I'll help you understand it better. So if you were to carry this lever all the way down, right, you would travel some distance, d. Let's call it d1. Yep. And this end would travel some shorter distance, d2. Now, we know from the law of conservation of energy that whatever work we put into the system, assuming that the system is ideal, the useful work that comes out should be equal, right? So the work we put into the system, right, should be equal to the work that comes out to the system, right? So if we apply this work to some distance of d1, let's just call this 20 newtons, okay? 20 newtons to some distance of d1, what we get out should be, of course, this, we're opposing this larger force, right? This 40 newtons, 40 newtons, some distance of d2. Now, in order for this to be equal, what we should notice here is that d1 is obviously larger than d2, right? So this here, it's like it's concentrating the energy into a shorter distance, allowing us to lift more weight, right? And the way it does that, or the property that describes that, the way they maneuver from this shorter this longer distance to this shorter distance is the movement ratio, or what we sometimes call as the velocity ratio. Okay? And that's equal to the distance traveled by the effort, so d1, distance traveled by the effort, divided by the distance traveled by the load, d2. We can kind of get an idea of what this velocity ratio is trying to describe, right? Now, another important property of the system, right, is efficiency. Let's go back over. We just did mechanical advantage. We know what that does, and velocity ratio. So this is how much do we gain and what's the trade-off, right? How much extra distance we have to travel in order to gain this little bit of leverage, right? These two interact. Okay? Good. Now, since most systems aren't ideal, right? Most systems aren't ideal, and they have these things called losses, right? And an example of a loss that we're all familiar with is friction, right? So let's look at an example of friction. Let's say we had a box, some box. Resting on the ground. Of course, having some friction. And we pushed it with a force of, say, 20 newton. 20 newton. But because of friction, the friction quantified based on the coefficient of friction is 5 newtons. So when these forces resolve themselves, we find that the box is essentially moving as if it was being pushed with 15 newtons of force, right? Because this 5 newtons from friction opposes this 20 newtons. Yeah. So the outcome is a 15 newton force moving this box. Now, how we would describe that in terms of efficiency is saying that, okay, let's say efficiency is how much work we put in, how much of that is translated into actual work, into useful work, into the work that actually moves this box and is not going into overcoming friction. Something like efficiency, right? Efficiency equal to the work we put into the system, right? and the useful work we get out of the system, right? Useful work we get out. Now, generally, we know the work in is equal to the work out in an ideal system, but in this case, it's plus losses, right? Plus losses. And the losses in this case is friction, right? So putting this in terms of numbers, right? We can say the work we get out, some 15 newtons.
Excuse me, sir.
Yeah.
The work out. This is the work done on the load.
Yeah, useful work done.
Okay, sir.
Yeah. Times some distance, whatever distance this travels, and the work we put in is 20 newtons times that same distance, right? Times that same distance. So if this travels 4 meters, then of course we had to be pushing it for 4 meters, right? So the D's would cancel out, and we'd end up with efficiency being 15 over 20, which is 3/4, which is 75%, right? We could say that this system, the efficiency is 75%. Now, how does this efficiency is obviously something useful, and we want to know how much of the effort we put in, right, is going into actually moving the thing, because we don't want to waste energy in using a very inefficient system, right? Because that would just be wasting here. If friction was 10 newtons or 15, and then this box would only be moving 5 newtons, right? But that would be very inefficient, and we'd be wasting 50 newtons. So it would be better to find a different system to move this box. Maybe put this on wheels than push it to overcome friction. Okay, now how does this relate to the mechanical advantage and the velocity ratio? Okay, so let's title it. Let's say efficiency is useful work done on the load, work out, however you want to label it. Right about efficiency. So the work done on load is of course the load, and the distance it travels. So the distance traveled by load, let's just call that D1, right? And the work in is the effort, right? The effort. Not to be confused with efficiency, times the distance traveled by the effort, right? So D2. So if we could notice that this part here, that's actually the mechanical advantage. So mechanical advantage, this part here is actually the inverse of the velocity ratio divided by velocity ratio. Let me open up this so you guys can see that. So the mechanical advantage is load over effort, right? And the velocity ratio is distance moved by effort divided by distance moved by load, right? So load over effort, as this part here, as this part here. So the mechanical advantage is easy, right? And the distance moved by the effort and distance moved by the load, so here, right? If this were distance moved by effort, which is D2, over D1, and since we're dividing, right, it's like multiplying by the reciprocal, so this would be this. You guys can see that. Let's create this format, I'm sorry. right? So we end up with the last formula. Efficiency is equal to the mechanical advantage divided by the velocity ratio. Or for in very more simpler cases, the useful work done, right? The work done divided by the work we put into the system, right? Work we put into the system. Now, keeping all this in mind, let's look at number 5. Any questions though on these three? Anything you guys don't understand? No? Okay, good. So number 5. So the diameters of the wheel and axle are 300 millimeters and 75 millimeters respectively. When a body having a weight of 300 newtons is being lifted, the efficiency is 80%. Calculate A, the velocity ratio, B, the effort required, C, the mechanical advantage, D, the useful work done when the load is raised 20 millimeters, and E, the corresponding work done by the effort. So first things first, what is a wheel and axle? Let's find a picture real quick so you guys could see what it is. Okay, so this is an example of a wheel and axle, right? So you see the wheel here is bigger and the axle is here. And based on the distance traveled by this, because since this is a longer distance, so we can use a smaller force spread out over a longer distance, concentrate it into this smaller distance to give us more force, right? Use the velocity ratio here to take advantage, to capitalize on that effect. All right? This is a wheel and axle. You can see it in other ways, like crank, for example. Something like this is another way to look at it, right? You guys can see. Something like this with a handle of the current, pirate chip. That's essentially what a wheel and axle is. Right, good. So now, how would we go about finding the velocity ratio with this? Well, let's look back at our formula. The velocity ratio is equal to distance moved by the effort divided by distance moved by the load. Let's look at it. So here, when we pull this rope down, or this maybe had a handle and we were turning it, right? We were turning it. The distance that would be moving by the effort would be the circumference of this thing, right? And the distance moved by the load as this rope wraps around here would be the circumference of this axle, right? So now, the formula for the circumference of a circle is 2 pi r, right? Not pi r squared, because that's the area, 2 pi r, or I times the diameter, because 2 times the radius is the diameter. So putting that into our formula, we know velocity ratio is equal to distance traveled by the effort, which is the wheel, so pi d, pi times the distance traveled by the wheel, which is 300 millimeters. That's the diameter of the wheel, right? and the distance traveled by the effort, the axle, distance traveled by the load, sorry, the axle is 75 millimeters, right? Using this formula, of course, the pi's cancel out. So for future reference, you can always just leave out the pi and divide these two because the pi is cancelled. But all systems might not be this way, and they might even cancel. All right, good. So dividing 300 by 75, we get 4. So the velocity ratio is 4. Easy. Plug it into the formula, get the answer. Now, what is the mechanical advantage? Now remember, mechanical advantage is related to velocity ratio through efficiency, right? Through the efficiency of the system, right? Because the work done divided by the work in, and when we translate this, efficiency, right? It was the same as efficiency. Okay, good. So we know we were given efficiency as 80%, and we just found our velocity ratio. We can use these two with this formula to find the mechanical advantage. So with efficiency being 80% or 80% or 0.8 per unit, is equal to the mechanical advantage, which is our unknown, divided by 4, our velocity ratio. Translating this formula, solving for the mechanical advantage, we get the mechanical advantage is equal to 4 times 0.8, which is equal to 3.2. 3.2, our mechanical advantage. And again, mechanical advantage, velocity ratio are both unitless terms, right? They're just terms that we use to describe the system. Okay. Now we also want to find the effort required to lift this 300 Newton weight, right? The weight being lifted is 300 Newtons. What's the effort that required to lift that? Well, we know the mechanical advantage is equal to the load we're trying to lift divided by the effort that we need. We just calculated the mechanical advantage by means of efficiency and velocity ratio, and we found it to be 3.2. Okay. Plugging that into our formula, with the load we're trying to lift, we get 3.2 is equal to 300 Newtons divided by the effort. Solving for the effort, we get the effort is equal to 300 Newtons divided by 3.2, which is equal to 93.75 Newtons. That's the effort. Now, any questions so far up to this point? No questions?
Excuse me, sir. So now, when you have the when you did the mechanical advantage, and you send over the 4 and it multiplying. So why you didn't do the same for the effort? When the 300 Newtons go over to the 3.2, it wouldn't be multiply. Why is it divided?
Is algebra, yeah, algebra. Okay, so 2 is equal to 4 divided by 2. 4 divided by 2 is 2, obviously, right? This makes sense, right? Yeah, so if we were to carry over this 4 and multiply, what would that give you? Half, and you can't carry over the 4, so 2 times 4 would be 8. That doesn't make sense, right?
Yes, sir.
Try and solve this equation by carrying over this 4. Doesn't really make sense, right?
Yeah, that's
Yeah, so this is algebra. This is dividing, so it must be multiplying. So the steps for this is 3.2 times the effort times the effort is equal to that 300 newtons. 300 newtons, right? Good. So now from here, they carry back over the 3.2. 3.2, right? Got that?
Yes, sir. Yes, sir.
Good. Algebra. All right. Okay. Now, D and E. This part involves work, right? So let's just remember formula for work, not the one we were given, but yeah, not the one involving efficiency, just the regular one. The work is the force, right? And whatever distance we put it. So the force, the work we put in, and for how long, right? It's how we quantify the way the energy is used, right? How much energy do we use? And of course, it's measured in joules. So the force, the work done, raise the load 20 millimeters, is the force we use, the force of the weight of the thing, for 20 millimeters. So what that just says is, in order to raise this load 20 millimeters, then we had to essentially apply 300 newtons of force for 20 millimeters. So the work done on the load is equal to 300 newtons times 0.02 meters, right? So remember, always convert back to your standard units, right? And that's equal to 6 joules. Joules, right? Joules. Newton meters, work measured in joules. Good. Now, we know that the work done on load, the useful work done on load, right? Useful work relates to the work done by the effort or the work we put into the system by means of efficiency. So the work done on load, useful work, divided by the effort, that's equal to the efficiency, right? We know the efficiency is 0.88% per unit. Solving for effort, we divide this 6 joules here by 0.8, and that gives us 7.5 joules. Simple, use the formula, plug it in. The same algebra we did here, right? Carry over, carry back over. Any questions on this? No. Okay. Moving on. Now, in a wheel and axle machine, the wheel has a diameter of 200 millimeters and the axle has a diameter of 40 millimeters. Calculate A, the effort required to lift the mass of 15 kgs if the efficiency is 0.9 per unit. B, the velocity ratio. C, the mechanical advantage. D, the ideal effort. And E, the effort to overcome friction. F, the ideal mechanical advantage. Okay. The first thing first, velocity ratio. We know pi d, it's a wheel and axle machine, yet again, right? So we know pi d, the pi's cancel out, so it's essentially just the diameter of the wheel divided by the diameter of the axle. 200 millimeters divided by 40 millimeters, so no need to convert. 200 millimeters divided by 40 millimeters is equal to 5. 5 is the velocity ratio. Again, unitless term, no newtons, no kilograms, no nothing. It's just a term that describes the machine. Now, let's hold a little bit on the effort while we find the mechanical advantage. Okay. Using the formula with efficiency that relates efficiency and velocity ratio, let's find the mechanical advantage in the same way. So with the efficiency as at 0.9 per unit or 90%, okay, the efficiency, we know that that is equal to the mechanical advantage divided by 5, the velocity ratio. Transposing this, we get the mechanical advantage is equal to 0.9 times 5. This into our calculator, we should get 4.5 as the mechanical advantage, just like the previous question. Now, let's go back to finding the effort required, part A, to lift the mass of 15 kg. Mechanical advantage is equal to the load divided by the effort. So the load that we're trying to lift from the question, 15 kg. Yep, 15 kg. kg. Now, of course, we need that in newtons, right? You don't just want to put 15 kg. So the load here would be 15 kgs times that gravitational constant, 9.81. The effort is, of course, our unknown, right? Effort and mechanical advantage, we just found it to be 4.5 with an efficiency of 90%. Plugging these values into our formula, we have 4.5 is equal to 15 times 9.81 divided by effort. Solving for effort, we get that the effort is equal to 15 times 9.81 divided by 4.5. Breaking this down, we should get the effort being equal to 32.7 newtons. Or 2.7 newtons, just like before, nothing new. The only thing new is that we converted 15 kgs using the gravitational constant, right, to weight. Now, the other part is a bit different from the previous question. Okay. So now part D says the ideal effort, and part E, the effort to overcome friction, and F, the ideal mechanical advantage. So usually when they say an ideal system, they mean a system without losses, a system where we're not wasting any energy overcoming friction, right? So what that translates to is efficiency at 100% or 1 per unit, unity. During electrical engineer, unity might mean something, might be a very popular word to use, unity. So 100% efficiency, the ideal system. Good. Now, for the ideal system, right, efficiency is 100%, so 1, right? Not 0.9, not 0.8, but 1, right? And that's equal to the mechanical advantage over the velocity ratio. Now, transposing this, we find something very unique. Find that in an ideal system, velocity ratio equal to the mechanical advantage. So we find our trade-off, which is the extra distance we have to travel as a factor versus the extra force we get are equal. These two are equal in an ideal system. So now the velocity ratio of any machine is set, or for a wheel and axle is set, right? Diameters aren't going to change, right? But friction is an unknown, and friction varies with the efficiency, right? So here would always be 5, and as efficiency goes up and down, mechanical advantage would change. So if the velocity ratio for this system is 5, then the mechanical advantage, the ideal mechanical advantage, ideal one, right? Not the one at 90% efficiency, which is this 4.5 that we calculated, right? This one here was a 90% efficiency. The ideal one is 5. 5 divided by 5 is 1. So that makes sense to us, right? So the ideal mechanical advantage, which is the same as the velocity ratio. Now, using the ideal mechanical advantage as 5, we can find the ideal effort. So using the ideal mechanical advantage as 5, mechanical advantage is equal to load, is your 15 kilogram load times the 9.81 gravitational constant, divided by the ideal effort, which is your unknown, which is what you want to find. So that is equal to the ideal effort is equal to 15 times 9.81 divided by 5, which is 3 times 9.81, which is 29.43, right? 29.43 Newton. And 9.43 newtons. Okay. Any questions on this little piece here?
Sir,
Yeah.
is it always that in the case of finding the ideal mechanical advantage,
Yeah.
it is always equal to the velocity ratio?
Yeah, unless the dimensions of the system changes.
Unless it changes. Okay.
Yeah. So you remember the velocity ratio is so in an ideal system, efficiency is 100%. We can agree on that. So as long as the velocity ratio is some number 8, right? And the mechanical advantage would be some unknown. Solving this formula for the mechanical advantage is 1 times A, which is just 8. So whatever that value is for the velocity ratio, it's going to be equal to the mechanical advantage, right? Unless, of course, the dimensions of the wheel and the axle change. Or in the case of a lever, maybe the length of the lever changes, okay? Now, the effort to overcome friction. Now, we know in the ideal system, we don't have any losses, right? And the ideal effort is 29.43. Now, in this system, remember this system isn't ideal, but we found for the ideal system anyway, because we want to know how much losses we get, right? Okay. So now, the effort we used in this system as 90% efficient, 90%, we calculated that, right? We calculated that effort as 32.7 newtons. So now, subtracting this 32.7 newtons from the ideal effort, right? We find how much of this is being lost to friction. And well, it turns out that's 3.27 newtons. That's how much is being lost to friction. 3.27 newtons. So we're just subtracting the two. We're subtracting the effort we actually use versus the ideal, and we're finding how much of it goes to friction. So this here is your losses, right? This is where the inefficiency comes from. That 10% that's missing, right? Okay, good. Right. Questions on this? What have we got? Now number 7, much simpler. Let me just read it for you guys, and then you'll work it yourselves. A simple winch. So you guys know what a winch is. It's the same thing as a wheel and axle, right? Simple winch has a drum 25 millimeters diameter around which a rope is wound. The handle, which operates at a radius of 400 millimeters, is connected directly to the drum. The winch is used to raise a body having a mass of 50 kg. Calculate A, the velocity ratio, B, the tangential effort required at the handle if the efficiency of the winch is 80%. Now, tangential effort, if we were to look at this closely, right, it's just a rope coming around the wheel. New. So it's just a rope coming around the wheel, right? That rope kind of lying somewhere like this, right? So as we pull this rope down from the wheel, the effort is actually being applied tangentially, right? And of course, as the wheel rotates, all the efforts are tangentially. So that's what this means. And if it were a handle, as we push the handle, it would also be applying tangentially, right? So the tangential part just really means we're going around like this, right? Applying the effort. Tangent. Now, keeping that in mind, and keeping that this says radius, right? Radius, not diameter, and this says diameter. You guys take 2 minutes, work this question out, and tell me if you get these same answers. Okay? Go. Was someone saying something? Okay, is anyone finished? No? Question hard?
So a couple seconds more.
All right, do you think?
Sir, I got what you got, sir.
Okay, good. All right. So, anybody got any questions? Find any difficulty working the question? Ask now. So,
No, sir.
I get it's straightforward. We take the two diameters. Of course, this is the radius, so we multiply the 400 by 2, right? This is 2
Yes, sir.
times 400. We divide that, and we get 3.2, right? Good. And that's our velocity ratio. Now, oh, yeah. So they gave us the efficiency as 80%, right?
Mm-hmm.
Yeah. Okay, yeah. So what we kind of skipped the step with the mechanical advantage and whatnot. But so let's just work out. So mechanical advantage is this weight, the load, divided by F. And this here is your velocity ratio. Velocity ratio. Right? So this here is your mechanical advantage part, right? Now solving for F with efficiency is 80%. So 80%, which is 0.8, going over, come back. We get F, right? Which is the effort, is equal to that weight, that load, divided by 0.8 times the velocity ratio, which is 3.2. Okay. 3.2. Or you could go about finding the mechanical advantage first, then finding this, right? Or I could just do this way. Good. That should give you 191.6 Newton, right? Easy enough. Right. So question 8. No questions on this, right?
Excuse me, sir.
Yeah.
Excuse me, sir.
Yeah.
At the last piece, we have F equals to the 50 multiplied by the 9.81, right?
Mm-hmm.
Now you're trying to find the I think that's the force, right?
Mm-hmm.
They're finding. So the force is weight over what we have here, F
Yeah.
over
So we can go ahead and do
velocity.
is find the mechanical advantage first, and then use that to find the effort, and it'll be much easier. So this here is a little shortcut,
Okay.
right? So let me go back up. I kind of didn't realize I put it like that. So remember we had W times D1 over F, which are the effort times D2, right? The two distances. And we found this, right? Mechanical
Yes, sir.
advantage, right? What that's equal to is the weight, the load, divided by the effort. Let's just call that F, right? Good. That divided by the velocity ratio. Now, simplifying this, because we got a fraction on top divided by velocity ratio, right? We can just simplify that down into W divided by F times the velocity ratio, right? And that's equal to this efficiency, right? Is equal to efficiency.
Okay, okay, sir.
Good.
So the
And
80%
using
is
this,
the effort, right?
we're using this. Yeah, F is effort. So using that little thing
Yes,
there.
sir. So
Yep. So the efficiency is equal to W over FVR. And then we just transpose and solve it. 3.2 is the velocity ratio. Right? Does it make sense? Or are you still lost?
so sorry. So wait, sir. So the 80% is which one? 80% is the
Efficiency.
efficiency.
So you remember
Okay,
is
okay.
efficiency is equal to, let me get a color here. The mechanical advantage, which is the piece we break down and we had a fraction on top, right? We had it as this, right?
Yes, sir.
And then we break it down, right? So that's the mechanical advantage divided by the velocity ratio. Efficiency, 80%, equal to the mechanical advantage divided by the velocity ratio. And then we want to solve for the effort. Yep. We want to solve for the effort, F. So we transpose. We, of course, know the value for W, our load, which is a 50 kg load times 9.81. So we transpose, right? We take the F over, we bring the 0.8 over. We get this thing. So that's essentially what's here, right? I skipped steps. Good. You understand now?
Yes, sir. Yes, sir.
All right, good. Okay. Yeah, it's if it's still too complicated, you know, use the general way. Find the mechanical advantage first, and then progress on to the effort. That way is fine also, right? No need to confuse yourself with this fancy new formula. But as long as you understand the principle, it's there and you can utilize it. Right, good. Moving on. We're finished with the wheel and axle, and we're going back to the inclined plane. But we're looking at it from a different perspective, from the system's perspective. We're looking at velocity ratio, which was the ratio between the distance we need to push this thing and how much height do we gain, how much useful work is done, right? Because inclined plane is something you might want to push a box or something into a truck, right? Something up. That's why it's an inclined plane, right? And you're pushing it some distance L, right? Some longer distance to gain height. Because of course you can't just lift a very heavy object straight up, so you might want to push it. And that's the purpose of the machine. Now with that in mind, let's work questioning. A block of concrete having a mass of 200 kilograms is hauled up an inclined plane having a gradient of 1 in 5. If the efficiency is 35%, calculate A, the effort required if its direction is parallel to the plane, B, the velocity ratio, and C, the mechanical advantage. All right. So remember, before we go to effort, we always want to find a velocity ratio first because it's easier that way. So now, velocity ratio is distance traveled by the effort divided by distance traveled by the load or useful work done. And in an inclined plane, we have some box or something, or in this case, a block of concrete, a 200-kilogram block of concrete, but let's say something we can push it. And we're pushing it along this length, right? Along some length L, up to here. So that's the distance traveled by the effort. And the useful work done, the distance traveled by the load, yeah, even though the load is traveling the same distance, but what we gain from it, right? The distance traveled by load would be equal to the height. And the gradient of this inclined plane is 1 in 5. So that means for every 5 units traveled along the length, that in return gives us 1 unit in height. 1 unit in height. So 1 in 5. Okay? So the velocity ratio is, of course, distance traveled by the effort, 5, divided by 1, which is 5. So the velocity ratio is 5. Now, different from the wheel and axle, we didn't have to do any things and then have the pi cancel out. We can just say that whatever the gradient is, if it's in relation to 1, then it's obviously just the length traveled for every 1 unit, right? That's the velocity ratio. So the velocity ratio is 5. Now, if efficiency is 35%, and I know 35% is a bit low for efficiency, a lot of friction is going on here, so that's why the system is a bit inefficient. Calculate the effort required if its direction is parallel to the plane. Parallel to the plane just means all the effort is being used to pull this thing up. None is being wasted, because that would affect the efficiency also. Okay. So again, if we're gonna find the effort, we might as well just find mechanical advantage one time, and then go on to the effort. Right, so with efficiency at 35%, mechanical advantage should be 5 times 0.35, right? So remember formula, our old but gold formula, the efficiency equal to mechanical advantage divided by velocity ratio. Therefore, the mechanical advantage is equal to the efficiency times the velocity ratio. Efficiency is 0.35 per unit, or 35%, and the velocity ratio is 5. Calculating this gives us the mechanical advantage as 1.75. Okay? Now, using the mechanical advantage to find the effort, we get 1.75, the mechanical advantage, is equal to the load, which is 200 kilograms, times the gravitational constant, 9.81, divided by the effort. Solving for the effort, we get the effort equal to the 200 kilograms times the 9.81 divided by 1.75. Plug this in their calculator, we should get 1,121 newtons. Yep. You know, it's a little bit different from the wheel and axle, but if you notice, we didn't do anything new. 5 divided by 1, efficiency, mechanical advantage, effort. Nothing. The only thing different is that the way we found their distances is a bit different. And that would vary from machine to machine. But it's always distance traveled by the effort divided by distance traveled by the load. Okay, good. Any questions? Before I move on?
No, sir.
All right, good. Now, okay, let's start working and then I'll go to that part. Number 9. Body having a weight of 3 kilonewtons is dragged up a surface inclined at an angle of 20 degrees to the horizontal. The effort acting parallel to the surface is 1.3 kilonewtons. Calculate A, the velocity ratio, B, the mechanical advantage, C, the efficiency, D, the work done in hauling up the body a distance of 3 meters, and E, the corresponding useful work done. All things we've worked before, but now it's for an inclined plane. Now, the unusual part with this question is they didn't give us the gradient. They say an inclined plane with an angle of 20 degrees. Let's look at that. Let's analyze that a little bit. So for number 9, they didn't give us a number like 5 or 1. We don't know what these values are. What we do know is that this angle here is 20 degrees. Let's generalize. Let's say, what if the situation was we always had an angle, right? They gave us some unknown angle, alpha. For some other questions, maybe you want to work number 10, number 25, number 103, and they give you alpha, right? So how can we develop an equation for that? Well, let's say, in this case, if the gradient is 1 in 5, the velocity ratio is 5. If the gradient is 1 in 4, the velocity ratio would be 4. If the gradient was 1 in 3, the velocity ratio would be 3. So we know as long as we put a unit here, as in a 1 here, and we translate to how much length we travel, then the velocity ratio should be the length of this thing, right? Should be this length, which is 5. As long as this is 1, velocity ratio equal to the length, VR. Right? Now, if this here, let's say the velocity ratio in this case was 1 in 5 here, and we the same gradient, but the height we travel is longer. It would be 2, right? So 2. Now, if the gradient is still 1 in 5, which is every 1 meter we travel 5 in length, the length here would be 10. 10. So the 1 in 5 would be somewhere around here. We'll put that in. So this here would be a 1, and this short distance here would be a 5, right? And then this here would be another 5, and then this here would be 1 and 1, and you would go up. So you find it, build upon it, right? So, and in the same thing, the gradient being the same, right? It would be 10 divided by 2 is still 5, right? So the gradient tells us what the velocity ratio is, or the movement ratio is. So as long as we can find that length, assuming here to be 1 unit, we'll find the velocity ratio. So let's assume here to be 1 unit, 1, let's find length. So sine of alpha is equal to opposite, which is opposite 1 divided by the hypotenuse, which is the length, right? Transposing this, right? Carrying this over, we get the length times sine alpha is equal to 1. And then solving for length, right? We get the length is equal to 1 over sine alpha. And this length here, L, is of course the velocity ratio, right? VR. Great. So we get this new formula for an inclined plane when they give us an angle. Now the velocity ratio is 1 upon sine alpha. Good. Keeping that in mind, let's work number 9. First things first, find the velocity ratio. And we already developed the methodology, right? Velocity ratio, mechanical advantage, efficiency. Okay, that's the steps we take. So velocity ratio, we know velocity ratio is equal to our formula. They gave us an angle 20 degrees. So 1 divided by sine 20, the velocity ratio is now 2.924. 2.924 as the velocity ratio. Just plug that into a calculator. Using, no, so they didn't give us the efficiency, but what they did give us is the effort. They gave us the effort. So we can use that to find the mechanical advantage and the efficiency. So we know mechanical advantage is equal to the load or the weight divided by the effort. Effort, call that F. And in this case, the effort is 1.3 and the load is 3 kilonewtons. So the mechanical advantage is equal to 3 kilonewtons divided by 1.3, which is 2.308. Plug that into a calculator and you should get the mechanical advantage. Okay. Now, the next part, they ask us to find the efficiency. We just calculated the velocity ratio and the mechanical advantage. Using those two, we can complete the formula for efficiency. Efficiency is equal to mechanical advantage divided by velocity ratio. The mechanical advantage is 2.308. The velocity ratio is 2.924. Dividing that, we find that the efficiency is 0.789 per unit, or 78.9%, or approximately just 7 to 9%. Okay. Now for D, the work done in hauling the body a distance of 3 meters, right? Okay, good. So the work done in hauling the body a distance of 3 meters, and E, the corresponding useful work done. So what they want here is the work done by the effort, the work we put into the system, and the corresponding useful work done. Okay, so we calculate the efficiency, so we can obviously calculate those two. So what we did, we applied the effort, which was given to us as 1.3 kilonewtons. To haul the body 3 meters, we applied it for 3 meters, right? Okay. So 1.3 kilonewtons times 3 meters is equal to 3.9 kilojoules, or 3,900 joules, right? Now, using efficiency, we can calculate the work done on the load, useful work done, right? Useful work done. useful. Efficiency is 79% or 0.79789, to be more precise. 789. Is equal to useful work done on the load, which is what we want to find, divided by the work done by the effort, right? The work we put into the system. Transposing, we get the useful work done is equal to that same 3.9 kilojoules times our efficiency in per unit, which is 0.789. That should give us 3.0771 kilojoules, or 3,077 joules. Any questions on this? No.
No, sir. No, sir.
Okay. Now, so another way to work this is, since we already have the load, right? The load was given to us as 3 kilonewtons, right? So let's look back at our inclined plane. So the load was given to us as 3 kilonewtons, right? 3 kilonewtons. Here, 3 kilonewtons. So another way to work this question would obviously be finding the distance traveled here, right? This h, by that 3 kilonewton load, right? Find what distance this went up, right? This obviously was a 1.3, this push here was 1.3 kilonewtons for some length 3 meters, right? 3 meters. 3 meters. So an alternative way to find it, and we know the angle here is 20. Yeah. An alternative way to find that is to find this length and just multiply 3 kilonewtons. Right? So 3 kilonewtons by whatever the length h is. That's 3 kilonewtons times times 3, which is the hypotenuse, times sine of 20. Let's just break out the calculator real quick. So sine of 20 times 3 times, what did I do? 20 sine of 20 3 times 3. So this here gives you 3.078. 78, obviously kilonewton. So this here is an alternative way to work this question. Not to confuse you, this is just an alternative method. You can always go about working it this way if you like. So that's all I have for you. Hope you guys learned something. If you didn't, I sent you guys a handout and you can always read the text. So if you don't have any questions.
Question, sir.
Okay, good, go.
Could you tell us whether there will be a test this week or not?
I don't know. I wasn't made aware of any tests.
The reason why I asked is because before we were closed off for the holiday, I overheard Miss Cecile saying that the first week of classes, when class will reopen back, there will be a test. But I'm not sure if that's still happening or not.
Okay, so prepare for a test then. That's what I would recommend.
Okay.
Prepare for a test. Yep. All right. Any other questions? No? All right, good. So that's the end of the class.
So the person just reminded you in this chat section to remind Miss.
Yeah. Okay, good. All right, good. So that's it.